Okay, so let's start the last lecture of the school. So let me first review what we did in the last 3 lectures. So we first discussed the ON model, and then I explained that the 2, 2, 2 S matrix of the ON model can be determined by imposing Yang-Baxter, unitarity, and crossing. And then we moved on to N equals 4 super mu theory, and then also discussed that the 2, 2, 2 S matrix of the spin chain describing a single trace operator of N equals 4 super mu theory can be determined by imposing using superconformal symmetry, and in addition, some large gauge transformation or large gauge symmetry. So the underlying themes of the topics that I explained so far is a philosophy of the bootstrap. So the idea is to impose some consistency conditions with some minimal inputs and then try to determine the answer without really doing the computation. So today, because this is the last lecture of the school and I guess you guys are all tired, so I decided to talk about a very elementary or very simple thing. So the title of the lecture today, so lecture 4, is bootstrapping quantum mechanics, quote unquote, bootstrapping quantum mechanics. And today's lecture will be largely based on the beautiful work which appeared recently and the authors are Katsushi Ito, Marcus Marino, and Hongfei Xu. And so I'm going to talk about this paper basically, but there is also a related paper which is, which discuss a slightly different topic, but they use the very similar techniques. And this is the paper by Aldai, Maudacena, and Sever and Viela, in which they discuss the scattering amplitudes in N equals 4 super mu theory. So what I'm going to do today is to basically give a review of this paper, but I'm also going to explain some computation that I did based on the results of this paper, which make the lecture a bit more thrilling because some of the computations I actually did this morning. So I'm not sure if that's completely correct, so you should keep suspicious throughout my talk. Okay, so that was the word of caution. So let me first start with the motivation. So let's talk about harmonic oscillator, which we all know and love. So harmonic oscillator. So then the potential is something like this, right? And then we know how to quantize the system, but we also know how to, for example, quantize the system using the Wkb approximation. In the Wkb approximation, what you need to do is to draw a line above the potential and the energy, and then basically compute the cycle, which is the integral of square root of E minus Vx, and then impose Bohr-Sommerfeld quantization condition. So this is the Bohr-Sommerfeld quantization condition. As you might know, for the harmonic oscillator, well, by the way, I think I had too much coffee for lunch, so that's why the curves are a little shaking. But anyway, so this, as you probably know, for the harmonic oscillator, Bohr-Sommerfeld quantization condition is exact. But of course, this is not the most interesting thing. And the more interesting thing is the double well, which also appeared in Gerald's talk several times. So in the case of double well, let's consider in particular this kind of double well, where the potential barrier I denote by B. And let's first consider the case where B is very large. And where B is very large, you can basically regard them as a 2 decoupled harmonic oscillator. And we can basically impose Bohr-Sommerfeld quantization condition for each left and right cycles separately. So this is the left cycle and this is the right cycle. But of course, this approximation is only correct when B is very, very large. And we know that for finite B, there is a tunneling effect, which connects two cycles or two vacua. And in particular, if you basically in the regime of like a very large, and if the double was symmetric, we know that basically like the ground states are kind of twofold degenerate because you can consider left ground state and the right ground state. But if you consider the effect of tunneling, the degeneracy is lifted. And what's important for the talk today is that this tunneling is also in a sense given by cycle, as you probably know. But now we need to consider this new cycle, which I call instanton cycle, or maybe forbidden cycle. And essentially the instanton effect is given by e to minus square root v minus e dx. Okay? So this basically, so what I just said is that when B is very large, there is a left and right cycle, and which are completely independent. But now, if you include the tunneling effect, then the new cycle starts playing a role, and it kind of connects left and right cycles. So this basically suggests that there is some interactions among cycles if you want to non-perturbatively quantize this system. And so the cycles that are relevant for the double well is, of course, the left and right and instanton cycle. And you can also phrase this using the word of resurgence, about which Gerald talked. And from the point of view of resurgence, what this really means is that if you start from this cycle and do the Wkb expansion, then the expansion is not Borel summable. And then that means that you discover some singularity in the Borel plane, and then the singularity is basically given by the instanton cycle. But I'm not going to use the language of resurgence in my talk, so this is just a parenthesis. And the goal of my talk today is to have a control over interaction among cycles. And the method that I employ is to use analytic properties in complex X and H bar. So what I mean by this is that usually when you solve the Schrodinger equation, you just consider the problem on the real axis, but in order to have the control over the interaction among cycles, it's actually important to consider the Schrodinger equation in complex plane X. And also, I'm going to complexify H bar. So that's the basic strategy that I'm going to take. OK, is this clear? All right, so let me start, but maybe I should pause a little bit. Maybe not. OK, so let me start. So now what I'm going to do is to derive some nice functional equation from the Schrodinger equation, functional relation. Okay. So it is a 4-step procedure. I think it's 4-step. And the step 1 is to rewriting Schrodinger equation a little bit. But this is actually just a trivial rewriting which changes the normalization and convention. So the Schrodinger equation you are familiar with have this shape, right? Vx minus E psi x equals 0. Okay, so this is the energy, and I just moved it to the left-hand side. And you can rewrite this equation by rescaling rescaling x into the following form. With minus zeta x plus x r plus 1. Okay, so I should have said that I'm going to restrict myself to the polynomial potential. So I'm going to assume that this v of x is polynomial in polynomial. So in that case, by rescaling x, you can always bring, by rescaling x and redefining h bar, you can always bring the equation to this shape. So this is the starting point of our analysis. And in a sense, this part is our new potential. So this part is our new potential, V nu x. And this zeta is our new h bar. Okay, so this is the starting point of our analysis. And furthermore, we do assume a little bit more. So we further assume R is odd. So remember, in my definition, the leading term is R plus 1. So R being odd means the leading term is even. Well, this is, of course, a necessary condition in order to have a well-defined quantization on the real axis, because otherwise there is a runaway direction at infinity. So this is just saying that our new V has this shape at infinity. And secondly, we also need to assume that all zeros of V of x is on the real axis. So this is actually a bit technical assumption. Probably you might not appreciate it at first sight. But okay, so let me call it the reality condition throughout my talk. But yeah, you don't need to worry too much about this second condition. This is really a technical condition. So the idea is to first assume this condition, and then you get some nice equation in the end, and then finally analytically continue the final result. So by doing that, you can actually go to arbitrary V of x. Okay, so these were my two assumptions. So basically, okay, so what I mean by this second condition is that, for example, if I draw V of x on the real axis, and if you see as many zeros as possible. So in this case, R plus 1 is 6. Okay. So this was the step 1. So let's go to step 2. So the step 2 is to analyze this equation at large x. But the important point is that we want to analyze this equation in complex x, so I just require that the absolute value of x is very large. So if you assume this, then your equation actually simplifies. So I always need to keep this differential piece, but for the potential piece, I just need to keep the leading order because they are subleading. The others are subleading. So this equation is easy to solve in the large X limit, and the result is given by this kind of exponential. So plus minus 1 over zeta, 2 over r plus 3, x r plus 3 over 2. Okay? And you should keep in mind, actually, there is a freedom of choosing signs. And this basically two different choice of signs corresponds to two different solutions. So remember, the Schrodinger equation is the second order differential equation, so generally they have two different solutions. And these two solutions, typically, one of them is exponentially large at large X, and the other is exponentially small. But which is large and which is small depends on the phase of X. So let me give you an example. So example is, again, harmonic oscillator. So harmonic oscillator is R equals 1 in my convention because the leading term in the potential is xr to r plus 1. So in the case of harmonic potential, then the equation that I wrote is given by this, 2 over x squared. And let me further assume that zeta is real. In this case, the whole complex plane can be divided into 4 different sectors. So first of all, it's clear that on the real axis, so this is the real axis. So this is the real axis. And on the real axis, minus solution is exponentially small, and the plus solution is exponentially large. And actually, this behavior continues in this 90 degrees region. And if you cross this line, then the behavior changes because that is easy to see if you consider the solution along the imaginary axis. Then in this case, plus is exponentially small, whereas minus is exponentially large. And on the other hand, and then you can do the same thing here. Now, again, you have minus small, plus large, and then you have plus small and minus large. Okay. So if you know the terminology of Wkb and resurgence, etc., these lines are called anti-Stokes line. But the name is not really important. And this region, each region, I'm going to call it Stokes sector. Okay? So I think this is clear enough, because this is just harmonic oscillator. So let me make 2 comments about this. So comment 1. So small solution, you can always define, the small solution is always well-defined. On the other hand, large solution is always ambiguous. So let me explain why it is ambiguous. So it is ambiguous because if you take some large solution, or a solution which grows exponentially large, then you can always add something that's proportional to the small solution, but the whole thing is still very large. So when you say some solution becomes large in some direction, this is not a well-defined definition for specifying a solution. Whereas if you say some solution becomes exponentially small in some direction, it is actually a well-defined definition of like choosing a solution. So because of this reason, in the rest of my lecture, I'm going to focus on this small solution. Okay? All right. So the comment 2 is what happens if I consider a complex zeta rather than real zeta. Of course, you can kind of easily expect what to happen. Well, you can easily imagine that like this whole picture should be somehow rotated if you give a phase to zeta. So that's the comment 2. So the comment 2. So suppose we do this phase rotation to zeta, then you can easily see that this phase rotation of zeta can be compensated by analogous phase rotation of x, but now the angle is theta over 2. So this is, of course, easy to see. If you look at the form of the wave function, the form of the wave function is 1 over zeta times x squared over 2 in the large x limit. So rotation by e to ic, so rotation of zeta can be compensated by half rotation of x. So, and if you carefully think how these lines gets rotated, then you can convince yourself that if I do this rotation, then this gets rotated in this direction by theta over 2. So this is interesting. In particular, this is very interesting when theta is pi. So yes, the theta is pi. And when theta is pi, then this means that actually the x plane gets rotated by pi over 2, which basically means that this, so you have like 4 region, but by the rotation by, so this is, these 4 region gets exchanged under the rotation zeta going to e to I pi zeta. Okay? So this is the comment 2. Of course, these comments were basically for this r equals 1 case, but I can, okay, so let me just draw a line. So this was the start of the r equals 1 example, and this is the end of r equals 1 example. But you can generalize this analysis to a more general potential, and more generally, zeta going to e to I pi zeta rotates sectors by 1 unit. So the picture you get is something like this. So in the case of, so for general R, you have like a bunch of sectors, and for each sector you can define some small solution. And then here you have S R plus 3 over 2, and here you have, well, here you have something. Okay, so this is the real line for zeta real. And using the property of, using this property that zeta going to e to I pi zeta rotates sectors by 1 unit, you can actually kind of get the relation like this. The small solution, take the small solution in case sector and rotates the phase, then you should get the small solution in the adjacent sector. And using this property, by iterating this procedure, you can basically relate S0, which is on the which is the sector on the positive real axis, and to SK, which is general small solution in general sector. And furthermore, we have freedom of choosing the normalization of each small solutions. So we can actually use this relation to define the small solution in the case sector. So you can define Sk zeta as 0 e to I pi k zeta. So this is our definition of small solution in the case sector. And there is one good thing about defining all these small solutions. So using these small solutions, you can actually state quantization condition of the quantum mechanical problem on the real line. So you can rephrase the quantization condition in this way. So when you have a well-defined eigenstate, so let's say you have energy eigenstate on the real axis, on x being real, then your solution, eigenvalue solution, so the eigenfunction must decay, psi must decay both at x equals plus minus infinity, because otherwise your solution is not normalizable. This basically means that when there is an energy eigenstate, say let's go back to this picture, S0, which is the small solution on the positive real axis, must somehow coincide with SR plus 3 over 2, which is the small solution on the negative real axis. So if you choose general parameters or general value of energy, this condition is not satisfied. Basically, imposing this condition selects the value of energy. So essentially, quantization condition, you can say that this is equivalent to imposing this. Is this point clear? Okay. So what this really means is that, remember our potential is Vx, our new potential was xr plus 1, and we had a bunch of numbers, like a k equals 0 to r, bk, xk. And in particular, b0 plays a role of energy. So what this condition means is that for generic values of b's, in particular b0, this condition that S0 is proportional to SR plus 3 over 2 is not satisfied. So by imposing this condition, you can basically determine, quantization condition determines or selects the value of B0. Okay? So now I introduce all the necessary ingredients to derive the functional equation. But to really derive a nice functional equation, I need to introduce yet another object, which is called the Wronskian. So let me, I think all of you probably know what the Wronskian is, but let me just give you a brief review of it. So let's consider our problem, and then consider two different solutions which satisfies this equation. Then Wronskian is defined by this equation. So I denote Wronskian by this angle bracket, and the definition of the Wronskian is given by this expression. And I also want to write it in this way, epsilon AB, psi 1 hat A, psi 2 hat B, and psi hat is defined as psi del psi, like a two-dimensional vector made up of psi and del psi. Okay, so this is just the definition of the Wronskian. And what is good about Wronskian? So the Wronskian is nice because this Wronskian if these like two psi's satisfy the same differential equation or same Schrodinger equation, you can actually show that this is independent of the position x. So it actually is just a function of zeta. Well, this is, of course, easy to show if you differentiate this definition. Differentiate this definition with respect to x. Another important property is that because it's a skew-symmetric product, if you take the same solution, you get 0. Okay? All right, so using this Wronskian, I can also rephrase, give yet another way of rephrasing quantization condition. So using this Wronskian, the previous quantization condition becomes just this simple equation. So in the previous equation, I claimed that the quantization condition amounts to requiring that SR plus 3 over 2 is proportional to S0. And if that's the case, you can easily see that because of the skew symmetry of the definition of the Wronskian, this Wronskian must be 0. Okay. So now we are already in a position to derive the functional equation. So to derive the functional equation, I just need one identity, which is the well-known identity for the epsilon tensors. AD, BC plus AC, DB equals 0. Okay, you can, well, just using the definition of the epsilon tensor, you can just like explicitly verify that this equation is true. And using this definition, and remember that Wronskian, in the definition of the Wronskian, you also get epsilon tensor. You can actually show that using this identity, you can derive this Wronskian relation, Si, Sj, Sk, Sl, plus Si, Sl, Sj, Sk, plus Si, Sk, Sl, Sj equals 0. So I think this kind of equality has various different names, but in my lecture, let me call it Plücker relation. So this is just the algebraic identity. Now, we are going to introduce our main object. Okay, so now we introduce our main object, which is called y function, which is defined in this way, y to j. So it has a different definition depending on the index, whether index is positive or negative. But when the index is, whether the index is even or odd. When index is even, I defined it in this way, s minus j minus 1, sj plus 1, over s minus j minus 1. Probably this is the most complicated and the most important equation for today's lecture. And for odd j, I define it in this way, s minus j minus 1, sj, s minus j minus 2, sj plus 1, and s minus j minus 2, s minus j minus 1, and sj, sj plus 1. But here, the main difference is that I evaluate this not at theta, but e to I pi over 2 times theta. I will explain why we need this kind of weird shift. Okay, so this is just the definition. Of course, at this point, it's not entirely clear why these are important, but I'm going to explain the physical meaning of these y functions soon. But before doing that, let me state an important property satisfied by these y functions. But before doing that, let me pause a little bit. Is there any questions so far? So the property, so let's call it theorem, is as follows. So so I will first write down the equation and then explain the meaning of it. And this weird notation is, actually I don't want to put, I don't want to put 1 here probably to further simplify the notation. So this basically is defined, so f plus minus is actually, it basically means the shift of the phase. Okay, so this is a theorem. So I claim that y's satisfy this nice functional equation. To require that y's satisfy this functional equation, I needed to shift the phase of odd y functions a little bit. But there is actually even more important physical reason why we need a shift, that's which I'm going to explain later. Okay. So this is actually simple to, in principle simple to prove. And the proof is essentially by applying Kluka relation. So it's a little bit of too much work to show this equation for general R. So let me just prove it for R equals 1, again for the harmonic oscillator. Okay, so the proof for harmonic oscillator. So for harmonic oscillator, let's first compute y equals y0. Okay, I guess you don't remember the definition, but if you look at the definition, then in the definition of y0, you have something like this. So you have something downstairs, but that's not important. But the important point is that in the definition of y0, you have s minus 0 dot s0, and as you know, minus 0 is 0. And so we have the Wronskian of the same wave function, which means that this is 0. So this actually tells you that y0 is 0. So this is actually true not just for R equals 1, but for general R. So let's now compute y1. So the definition of y1, so remember, okay, so let me first write down that expression and give some remark. So this is the result of my definition of y, and we need to remember the phase is shifted a little bit. Okay? And now, so this y1 is non-trivial, as you can see. So now let's consider y2. To y2, I have something like s minus 1, s1, and s minus 2, s2, and something downstairs. But we need to remember that in the case of R equals 1, there are only 4 sectors. So you have s0 here, s1 here, s2 here, and s3 here. Or depending on how you define it, it's kind of proportional. It's basically proportional to s minus 1. And in particular, s2 is proportional to s minus 2, because if you go in this direction twice, and if you go in the other direction twice, you get the same Stokes sector. This basically means that this is 0, so y2 is also 0. So in this particular case of harmonic oscillator, you only have one y. So because of that, the functional relation, which you need to verify, just reduces to this equation. So let me just remind you that original functional equation had this like a right-hand side, but because like almost everything is 0, I just need to show this equation. And it's actually easy to show. So remember that there is a shift by I pi over 2. And this shift is canceled by this minus. So for y1 minus, it's actually simple to express what it is. So we just need to take this expression, s minus 1, s0, s minus 2, s1, over s minus 2, s minus 1, s0, s1. Okay. And for y1 plus, there is original shift of e to I pi over 2, and then additional shift of e to I pi over 2, and they add up to the shift of e to I pi. And I don't know if you remember it, but I claimed previously, if you shift theta by e to I pi, you basically rotate the Stokes sector by 1. And that's, therefore, what I get is something like this. So I just need to put plus 1 for all the index. And s minus 1, s0, s1, s2. Now, I think we can immediately see some cancellation. So this and this are the same, and this is the same. And furthermore, I claim that s2 must be proportional to s minus 2. So let's call the proportionality factor alpha. So then I can cancel this and get minus alpha because the order is swapped. And then I get this, and then I again get minus alpha downstairs. So I get 1. So this is a simple manipulation. Okay, again, this was for r equals 1, but you can actually show the functional equation generally for general R. And if you do that, what in general, for general R, you actually get a chain of y's. And you can actually always show that y of r plus 1 is 0, and y of 0 is 0. So for general potential R, there are only R non-trivial y functions. And they have something like, they are like a constrained by some kind of like a functional equation which have nearest neighbor interaction. Okay. So far I defined weird y's and derived some weird equation satisfied by y's. So now I need to ask what is the physical meaning of those y functions. So that's the key point of my lecture today. But is there any questions so far? Okay, so let's proceed. So the physical meaning so there are two different approaches to understand the physical meaning. So one is to use the Wkb approximation. So let's again consider r equals 1 case first and consider this function, which is the only non-trivial one. For some reason, I wanted to shift the value of theta. Okay? And then let's just do the Wkb approximation for these y functions. So for that, I need to know the approximate form of the wave function. And so the small solution living on this sector is S0. And S0 can be approximated by this expression. So So this is just a standard Wkb. Okay? And so in the case of r equals 1, this v of x is something like x squared minus energy. Well, let's consider the simple case of where there is no linear term. But this is something like x minus e. And this, what is this z0? I took z0 to be a point in the Stokes sector and whose absolute value is very large. And I chose this initial point because otherwise the Wkb approximation is very, or the notion of small solution relies on the a large x expansion. So I better choose the initial point to be very large. And similarly, I can define the small solution here is -1, and in this way. And remember that in this region, the small solution, we need to choose a plus sign, and the expression gives you this. So the computation gives you this. Okay? And now, using these solutions, you can compute the Wkb approximation of the Wronskian itself, and it's simply given by something like this. Okay? So now we know that essentially y functions are just the ratio of Wkb, ratio of Wronskians. To understand what this means, let's just again draw a circle and put points. Here you have z0 and z minus 1 and z1 and z2, or z plus minus 2. And I showed that s minus 1 S0, Wronskian of s minus 1 S0, which appears here, gives you a contour integral from z minus 1 to z0. And if you do the same thing for here, s minus 2 S1, you get a contour integral like this. And you can also do the approximation for the denominators. Then, taking into account that it's the denominator, you get the contour integral like this. And then you get the contour integral like this. And remember that this square root of v actually has a branch cut, because this is essentially something like x squared minus e. So this basically means that you can basically shrink this contour to an integral around the branch cut of this v. And furthermore, going to the standard definition, you can, by carefully taking into account minus sign, you get something like this. Okay, so if v is x squared minus e. Okay? So now we have something very familiar. Clearly, this is the cycle. This is the quantity which appears in the Bohr-Sommerfeld quantization, and this is the Bohr-Sommerfeld period. And nicely, we have I here. And the reason why I have I here is because essentially I shifted by minus. So if I didn't do any shift, then what I would get is minus 1 over z plus some period, which is positive. So remember that for the definition of odd y's, we actually needed to do the phase rotation by e to I pi over 2. And essentially, the reason why I wanted to do so is to make y's evaluated on real theta to be exponentially small. Okay, so this was another reason why I wanted that shift. But anyhow, this, I think, clarifies the meaning of y's. Essentially, the point that I wanted to make is that y, the non-perturbative or quantum period Bohr-Sommerfeld period. So this becomes even clearer when you consider the double well potential. So let's consider the double well potential. And then let's consider, so now in this case, we have two branch cuts, right? And these basically correspond to r equals 3. So we have more Stokes sector. And if I draw the Stokes sector using a big circle again, then it becomes something like this. So there is a line cutting different Stokes sector. So this is the Stokes sector 0, and this is Stokes sector 1, and this is Stokes sector. There are too many dashed lines, and it might be hard to see, but 4 and 5. And if you follow the definition of y's and then compute do that Wkb approximation, you discover that these two lines correspond to y1, that these two cycles correspond to y1 and y3, whereas this line corresponds to y2, which corresponds to instanton cycle. Okay? So essentially, the functional equation that I derived earlier precisely captures how different cycles interact with each other. Okay, so far so good? So there is yet another understanding of, there is yet another important property of y function. And actually, y functions governs the quantization condition. Okay, let me again start with r equals 1. So in the case of r equals 1, let me yet another write the same expression. S1, S minus 2, S minus 1, S0, S1. And so remember that different S's are defined in this way for different Stokes sectors. So I claimed previously the quantization condition is the same as imposing that S minus 2 is proportional to S0, and also it should be proportional to S plus 2 because it's living on the same Stokes sector. And if you impose that, then essentially, okay, first of all, you can replace this by S2 and this by S2, and S0 also becomes proportional to S2, and this also becomes S2. Then you can show that if the quantization is satisfied, quantization condition is satisfied, this becomes minus 1. So the quantization condition, you can beautifully state it using y function, and which is nothing but this expression. Okay, maybe it's even more beautiful if you write it in this way. Okay. Well, yeah, it depends on your taste, but. And I claim that y's are essentially, like a log of y is essentially like a Wkb period or a Bohr-Sommerfeld period, but so this is nothing but the restating the usual Wkb quantization. Of course, this is not very impressive because it's just harmonic oscillator, but now I'm going to show something even more surprising and nice. So now, double well. All right, so let me remind you that double well is this. So you can play the same game and show that this combination, so I take, okay, so let me remind you that y1 is associated with this cycle, and y2 is associated, y3 is associated with this cycle, and y2 is associated with the instanton cycle. And if you take this ratio using Plücker relation, I get S minus 1, S3, S1, no, S0, S2, S minus 1, S0, S2, S3. And here, the quantization condition applied to in this double well case is to require that S0 is proportional to S3. Let me impose that. Again, I get -1. Now, there is actually use of rewriting this expression. So let me just rewrite it. Okay, let me go to yet next page. So let me rewrite it. So if you rewrite it, then the quantization condition becomes y2 plus 1 plus 1y, y1, 1 plus y3 minus equals 0. Right? And so this equation actually captured all the physics of the double well potential. So let me remind you that y2 is associated with the instanton cycle. So in the Wkb limit, or in the small h bar limit, in the leading approximation, it's exponentially small. So let's first ignore this y2. Then you can see that this equation factorizes into two equations, 1 plus y1 equals 0, or 1 plus y3 equals 0. So this is precisely what I explained in the beginning. So if you forget about the tunneling effect, then actually the problem splits into two decoupled harmonic oscillator. So this is what happens if you neglect y2 in this equation. But in reality, you cannot really neglect y2. And this equation basically connects the problem governing y1 and the problem governing y3 and makes it into a non-perturbative quantization condition. So this is quite beautiful, but there is a word of caution. Okay, so you should be suspicious about this. But I think it's okay, but anyway. So, okay, if you are suspicious, you should just go back to the definition of y's and you should check by yourself. Okay, so this is quite nice. So this basically tells you that once you can solve the functional equation that I gave you, you can basically solve the non-perturbative quantization problem. Okay? So let me finally explain how to solve the functional equation. But before going to that point, is there any questions so far? Okay. 3, solving functional equation. So this is just really how to solve this functional equation. So now everything boiled down to the mathematical problem of solving this equation. By the way, this equation is called Y-system equation, and it first appeared in a completely different context of understanding the finite size spectrum of integrable models. More precisely, the spectrum of the integrable quantum field theory on a cylinder. It's rather surprising the same equation shows up magically in this Schrodinger equation. So let me explain how to solve this equation. The first step, take log. The second step, okay, so if you take log, you get this expression. And you should remember that these ys in the Wkb approximation is given by zeta times something. Let's recall them. Let's denote it ms. This is essentially Bohr-Sommerfeld period. And I defined it in such a way that they are all positive. And the next thing I'm going to do is to remove this Wkb part from y's. So let's define. So I will tell you why I need to do this later. But for the moment, let's just define it this way. So by doing this, you basically remove Wkb part of the y function. Okay? Now, using this ls, you can rewrite the previous functional equation in this way. You might think that there might be some extra piece which take into account this shift, but it turns out this part is actually a solution to the homogeneous equation. So essentially, this is rotation by I, and this is rotation by minus I, and it cancels out. Okay? All right, so now I rewrite theta in this way and define theta, new parameter theta, which I call rapidity. Now we are getting closer and closer to integrable models. So the next step is to consider the kernel like this. Kernel. And consider convolution. K ls plus ls minus. Okay, I'm going to explain what I mean by this, but basically what I'm going to do now is to convert the left-hand side into just ls. And I claim that this can be done by this convolution. And let me just write down the definition of the convolution explicitly. ls plus ls minus equals minus 2 pi dy cos theta minus y over ls y plus I pi over 2. Of course, this is just the definition of ls. ls y minus I pi over 2. So this integral is along the real axis of the y-plane, and the integrand contains ls plus and ls minus, where ls plus and ls minus are just like a usual ls, but the arguments are shifted. And the next step is to split the integral to this piece and this piece, and then just like rewrite it as the shift of the contour rather than shift of the argument. If you do so, then you can actually split the integral in this way. So now this becomes this, and this is the part describing ls plus, and this is the part describing ls minus, and this is the real axis. Okay, is this point clear? And furthermore, I claim that you can also close this contour at infinity, and then finally the expression gets converted into this expression. ls of y. Okay. So actually, the reason why I needed to remove the Wkb part is because I wanted to make sure that I can add this part and this part. So this is the essentially theta plane, and this part corresponds to theta going to 0, and this part corresponds to theta going to infinity. But if I had Wkb part, which blows up around theta equals 0, around like this, then I wouldn't be able to close the contour because the contour doesn't die off at infinity. So that's why I wanted to remove this part. Okay? So once I remove this part, then this is a perfect closed contour integral. And now, so this is shifted by I pi over 2, and this is shifted by minus I pi over 2. And now you can really close the contour, and When y is something around here, then you really just close the contour and finally get ls of theta. All right? Is this point clear? Sorry? Yeah, that's a good point. Thank you. Yeah, sorry. So this is the theta. So let's say theta is around here. And let me just say, when shrinking the contour, I assumed that ls of y doesn't have any pole inside the strip, right? Because otherwise, I would get yet another contribution coming from the pole. So this was the origin of the reality condition. So I'm not going to explain why these two are related, but I just say that the reality condition that I made in the beginning was needed for this purpose. And actually, for theta equals 0 limit, you can easily show it by Wkb. Okay, so this was just a remark. And once you understand it, then it's clear what we need to do. So I just claim that k star ls plus ls minus is just ls. And we also know, because of the functional equation, this is k star log of 1 plus ys minus 1 plus log of 1 plus ys plus 1. And going back to the definition, the relation between ls and log of y, I can finally write down some nice functional equation, which is of this shape. Yeah, I guess you understand what you need to put here. Okay, so this is my final formula. Okay, so let me just explain the meaning of each part. So the leading part is just like a Wkb. So if you go back to definition of theta, then it's just like ms over theta. And subleading part is really the instanton-like correction, because I said somewhere that these y's in the Wkb limit is exponentially suppressed. So if you expand these logs, then you generate a series of y's, and each term basically gives you some like a non-perturbative correction. So this is the integral equation, which basically automatically generates all the resurgent series of our problem. And and I should say that, well, it's actually easy to solve this equation numerically, because you just need to use this as the input and then recursively iterate this equation. Okay. So finally, let me end my lecture by rederiving the harmonic oscillator spectrum. Now it's very simple. We have everything. For harmonic oscillator, you can easily see that this integral equation trivializes because you only have one y. So then what you get is actually log of y1 is minus ms e2 plus theta. So this is just saying that this is a Boas-Zolman-Ferrari period. And this is just saying that, like, for harmonic oscillator, like a Wkb expansion or Wkb approximation is exact. And then if you plug in it into the quantization condition, you finally derive nicely this equation. And I should just say that this plus 1/2 is coming from plus 1 here. So if you move it to the other side, it's minus 1. That's why you have plus 1/2. Okay, so we finally rederived the exact spectrum of the harmonic oscillator. But of course, the beauty of this formalism is that you can actually apply this to more general potential, including the double well, and then derive the non-perturbative series, which is basically the resurgent series. By the way, okay, so this is called, by the way, called TBA equation. So basically, that's the end of my talk, but let me just comment on several future directions that might be interesting to explore. So one possible interesting direction is to consider the case where you have susy. So although we are just talking about 1D Schrodinger equation, in some cases that potential is coming from the superpotential and the system has a secret supersymmetry. And in that case, we basically know exactly the ground state spectrum. And furthermore, there is a kind of nice generalization of the usual supersymmetric quantum mechanics, which is called n-fold susy quantum mechanics. And essentially, the difference is that, so in the usual susy, you have like a Q and Q dagger, and you get H on the right-hand side. But now, in the n-fold susy, you have Q and Q dagger, and you have some polynomial of H. In this n-fold susy quantum mechanical system, you can actually determine the energy of the ground state, not just ground state, but up to nth excited state, exactly. So by studying this kind of system, maybe we can understand some nice interplay between this kind of like a resurgence property and supersymmetry. And yet another application is probably large central charge conformal block. Probably some of you know that when you want to compute the large central charge conformal block, there is a nice method called monogermy method, which basically boils down reduces the problem to solving some kind of Schrodinger equation. And in that case, potential is given by some classical value of the stress energy tensor. And of course, if you want to consider real conformal block, then you need to consider potential, which have like a double pose at several positions. And what I consider today doesn't really correspond to that, but it presumably corresponds to what people call irregular conformal block. Understanding the relation more precise is very interesting, and also trying to generalize this analysis to the real conformal block would be also very interesting. So, okay, so that's all what I wanted to say about this. So is there any question? Well, it's just a Schrodinger equation, but I don't know any like other, like whether this appears from some other setup.
It looks like you skipped all the proportionality factors.
Yeah.
Does that matter?
Well, you can carefully keep track of the proportionality factor, but even if you keep track of it, you can show that it's actually -1.
But are they determined, or you can just set them in any way you want?
It's basically determined because I defined Sk by rotating S0. So once you determine the normalization of S0, normalization of Sk is also determined. But I actually didn't need to compute it in order to show these equations.
Actually, I just have a very small speculation. So for integral systems, which can be put into a lax form, you can define tau function. And tau function satisfies some bilinear identities, which can be interpreted as some Puig embedding of Grassmannia into the projective space. So here you also have some Puig relations, so maybe there's some connections between the two setups.
Okay, so you're asking about the equation for Y
or the
function?
S, actually. I mean the S satisfies some Puig relations.
Puig relation. Okay, so yeah, so essentially, so the Wronskian itself in the integrable quantum field theory context, the Wronskian corresponds to what's called T function. And T function is actually direct analog of the tau function.
I see. Okay.
What happens when the potential is not polynomial?
Well, that's a good question, but that's probably an open question for future research. Yeah, well, so for example, if you want to understand real conformal block, you need to add poles in the potential. So that's also beyond what I discussed today, or actually what they discussed in the paper.
More questions? Okay, well, the school has not ended yet. We have a Q&A session to follow, and we may have some extra events tomorrow. But since the lectures are over, let's thank all the speakers for great lectures.